car tire, 3,500 pounds, nearly 1,600 kilograms, rolling forward at 60 miles per hour, 100 kilometers per hour. Beneath it, something small, motionless. A beetle, half an inch long, about 1 centimeter, weighing less than a paperclip. The tire hits. Metal meets exoskeleton. The beetle should be pulverized, crushed into fragments, but it's not. This is the diabolical ironclad beetle, found in the deserts of North America, a creature that defies the laws of physics. Its shell can withstand forces 39,000 times its own body weight. No other insect comes close to this level of protection. Engineers have been studying it for years, trying to crack the code. How does something this small become virtually indestructible? The answer lies in an exoskeleton that evolved over millions of years, a biological armor that breaks every rule of insect design. To understand this beetle, we need to go back, way back, to when insects first developed hard shells. 400 million years ago, insects colonized land. They needed protection. Exoskeletons were the solution evolution chose. Most insects have wings, flight muscles, lightweight bodies optimized for movement through air. This beetle gave up all of that. The ironclad beetle belongs to a family called Zopheridae, bark beetles, living in tight spaces between rocks and wood. In the deserts of California, Arizona, Mexico, where temperatures swing wildly, where predators crush prey between powerful jaws. This beetle's ancestors faced a choice: fly away from danger or become too tough to kill. They chose armor. Over millions of years, wings fused together. Flight became impossible. But something extraordinary happened to the shell structure, the elytra, the hardened wing covers that protect most beetles. In this species, they transformed into something else entirely. These aren't just thick plates, they're a complex composite material, layers upon layers of precisely organized structures. The beetle is small, half an inch, 1.3 centimeters, but its armor is disproportionately engineered for maximum strength. It lives under bark, between rocks, in crevices where larger predators try to crush it. This is a beetle built for compression. Most beetles crack under pressure. Their shells fragment, shatter into pieces. This one doesn't break, ever. Scientists tested it, applied force gradually, measured exactly when the exoskeleton would fail. It took 39,000 times its body weight. For comparison, a human could withstand maybe 3 times their body weight before bones break. This beetle handles 39,000 times. That's equivalent to a 150-pound person, 68 kilograms, supporting over 5 million pounds, 2.3 million kilograms. The beetle weighs 0.003 ounces, less than a tenth of a gram. It can handle over 300 pounds, 136 kilograms. When a car tire hits it, the beetle survives. Not just survives, walks away completely unharmed. No cracks, no damage. So what makes this possible? The secret isn't just thickness, it's architecture, geometry at the microscopic level. The shell is made of chitin and proteins, the same materials other insects use, but arranged in a completely different way. Under a microscope, the structure reveals itself, layers stacked like plywood, each layer rotated at precise angles. This is called a helicoidal structure, spiral staircase arrangement of fibers, found in the toughest natural materials on Earth. But the ironclad beetle takes this further. It adds something no other insect has, a puzzle piece connection system. Where the 2 wing covers meet down the beetle's back, there's a seam. Most beetles, this seam is a weak point. Predators target it, pry it open, split the beetle in half. But not this one. The ironclad seam is reinforced, interlocking structures like jigsaw pieces. They distribute force across the entire shell. When pressure hits one point, the puzzle pieces redirect it, spread it out. No single location bears the full load. Here's where it gets strange. Scientists at UC Irvine wanted to know exactly how this works. They needed to see inside. Standard X-rays weren't enough. The structures were too complex, too densely packed. They needed advanced imaging. Micro-CT scans, three-dimensional X-ray imaging at microscopic resolution, revealing every layer, every fiber, every connection point. What they found was a biological jigsaw puzzle. The seam where the wing covers meet contains blade-like structures. These blades interlock, left side fitting into right side, creating a mechanical bond stronger than any glue. The geometry is precise, engineered to nanometer accuracy, each blade tapered, shaped to distribute stress optimally. When force compresses the beetle, the blades grip tighter. The harder you push, the stronger the connection becomes. This is the opposite of most biological joints. Usually, pressure causes separation, failure. In this beetle, pressure creates strength. But there's more. The blades themselves are layered, not solid chunks of chitin. They're laminated composite structures. Under electron microscopy, you can see the layers, thin sheets stacked and rotated, each one oriented at specific angles. This prevents cracks from propagating. When a crack starts in one layer, it hits the next layer at an angle and stops. The crack can't continue straight through. It would have to change direction, consume more energy. Most cracks just die out. Engineers call this crack deflection. It's used in bulletproof glass, in armor plating, in aircraft fuselage design. The beetle evolved it naturally, through millions of years of predator pressure. Every generation, the ones with better joints survived. Now, here's where it gets truly bizarre. The puzzle pieces aren't uniform. They vary in shape along the length of the seam. Near the head, the blades are shorter, more numerous, allowing slight flexibility for movement when the beetle walks. Toward the rear, the blades are longer, fewer in number, maximum strength where the shell needs rigidity. This is gradient engineering, varying properties along a structure to optimize for multiple functions. Nature did this millions of years ago. Human engineers only started using gradient design in the 1990s. For space shuttle heat shields, for joint replacements. The beetle had it perfected long before humans existed. An optimization algorithm written in DNA and tested through natural selection. Scientists ran computer simulations, modeled the stress distribution when the beetle is compressed. The results were shocking. Maximum stress occurs at the seam, exactly where the puzzle pieces are located. The beetle's armor is strongest precisely where it needs to be. Remove the interlocking blades digitally. Run the simulation again. The shell fails at 1/10 the force. The puzzle pieces increase strength tenfold. But it's not just the puzzle. The shell itself has a secret. The layers aren't all the same thickness. Outer layers are thin, flexible. They deform slightly under pressure. This absorbs initial impact energy. Inner layers are thick, rigid. They provide structural support, prevent catastrophic collapse after the outer layers compress. This is exactly how modern body armor works. Soft outer layer to catch the bullet, hard inner layer to stop penetration. Kevlar vests, ceramic trauma plates. The beetle has both, integrated into a single 0.5 millimeter thick shell. 0.5 millimeter, 0.02 inches, thinner than a credit card, yet stronger than most engineering materials at that scale. The shell's density varies too. Denser material near stress points, less dense material where flexibility is needed. Measuring this required precision instruments, nano indentation tests, pressing a microscopic needle into the shell, measuring resistance at thousands of points. The data revealed a strength map. The shell isn't uniform armor, it's a strategically reinforced composite structure. Strong where predators bite, slightly softer where the beetle needs to move. Every square micrometer optimized for its specific function. Now, what about the actual crushing event? What happens in the milliseconds when a car tire hits the beetle? High-speed cameras captured it. filming at 10,000 frames per second, slow motion, revealing the mechanics of survival. The shell compresses, but only slightly, maybe 5% of its height. That's 0.025 inches, half a millimeter. That tiny compression is enough. It spreads the impact over time, reduces peak force. The beetle experiences a slower, gentler squeeze. Compare this to an egg. Hit it fast, it shatters. Squeeze it slowly between your palms, it can hold surprising weight. The ironclad's shell turns a fast impact into a slow squeeze. Physics working in the beetle's favor. After the tire passes, the shell springs back, returns to original shape. No permanent deformation, no cracks, perfect resilience. This is elastic deformation. The material bends but doesn't break, stays within its elastic limit, springs back every time. Most biological materials can't do this repeatedly. Bone breaks, teeth crack, shells shatter. This beetle's armor recovers completely. Scientists tested it hundreds of times. Same beetle, same compressive forces. The shell never failed, never showed fatigue. Fatigue resistance, the ability to withstand repeated stress without degradation, critical for any structure that must survive daily threats. The beetle faces these threats constantly, predators stepping on it, rocks shifting, debris falling. Every day is a compression test. And it passes, every single time. The armor doesn't wear out, doesn't weaken, maintains full strength throughout the beetle's life. The beetle lives for years. Some estimates suggest up to 8 years. That's thousands of potential crushing events survived. But what's the cost of this armor? There must be a trade-off. Nothing in biology is free. The cost is mobility. The beetle can't fly, can barely run, moves slowly across the desert floor. When threatened, it doesn't flee, can't flee. It simply stops, pulls its legs tight against its body, and waits. Here's what makes this truly extraordinary. The beetle isn't just tough, it's using its shell as a weapon. When a predator tries to eat it, the beetle becomes a problem. Can't be crushed, can't be broken, can't be digested. Birds try to swallow it. The hard shell passes through their digestive system completely intact. The beetle emerges alive on the other end. Lizards bite down. Their jaws can't generate enough force. They give up, spit the beetle out, move on to easier prey. Rodents try to crack it like a nut. Their teeth can't penetrate. Some actually break their teeth trying. The beetle has become inedible. Not through toxins, not through camouflage, through pure mechanical invincibility. This is defensive armor taken to its absolute extreme. Evolution pushed to the limit of what's physically possible. Engineers tested the shell's toughness against known materials, compared it to industrial composites. The results shocked the research community. Pound for pound, the beetle's shell is tougher than some grades of steel, tougher than aluminum alloys, approaching the toughness of titanium. A biological material, grown at room temperature, using only proteins and chitin, matching metals that require furnaces and industrial processes. This has massive implications. If we can replicate this structure, we could create ultra-strong materials without extreme heat or pressure. The research team is already working on it, developing synthetic composites based on the beetle's jigsaw joint design. Early prototypes show promise. Composite panels with interlocking structures. They're significantly stronger than conventional designs. Potential applications are everywhere. Aircraft fuselages, body armor, automotive safety structures, building materials for earthquake zones. Imagine a car that could survive a collision and immediately return to its original shape. No permanent damage, ready to drive away. The beetle does exactly this, every day. And the secret is in the geometry, the puzzle pieces, the layered structure. But here's the most remarkable part. The beetle doesn't need repair mechanisms. The shell never breaks, so it never needs fixing. Human materials fatigue, develop microcracks, eventually fail. We build in redundancy, safety factors, planned replacement schedules. The beetle needs none of that. Its armor is so well designed that it simply doesn't fail. Ever. Tests pushed it to the absolute limit, 39,000 times body weight. That's where the testing equipment maxed out, not where the beetle broke. Scientists still don't fully understand every aspect of this armor. New discoveries emerge with better imaging technology. Recent studies found that the shell's microstructure varies seasonally. The beetle reinforces weak points as it ages. This suggests active maintenance at the cellular level. The beetle is constantly optimizing its armor, even after it stops growing. Researchers are now investigating the proteins involved, how they self-assemble into these precise structures, the genetic instructions behind the architecture. Understanding this could revolutionize material science. Imagine materials that self-assemble, self-optimize, self-repair if needed. The ironclad beetle represents a design philosophy, maximum strength through optimal geometry rather than through sheer mass. This is the future of engineering. Lightweight structures, high performance, minimal material use, exactly what nature has perfected. The beetle weighs almost nothing, uses minimal resources to build its shell, yet achieves protection that rivals our best technology. And it does this without factories, without energy input beyond what the beetle eats, without waste products or pollution. Sustainable manufacturing, circular economy, biomimetic design. These modern concepts, the beetle has been doing them for millions of years. Current projects are scaling up, from microscopic joints to human-scale structures, bridges that use puzzle piece connections, buildings that resist earthquakes through geometry. The military is interested, the aerospace industry is interested, medical device companies are interested. Everyone sees the potential. But we're still learning, still discovering. Every new analysis reveals another layer of complexity, another brilliant solution evolution found. The beetle's armor is a masterclass in mechanical engineering, taught by natural selection, written in chitin and protein. Evolution doesn't follow blueprints. It finds solutions through trial and error across millions of years. The ironclad beetle is proof that the best designs emerge from the harshest challenges. Pressure creates innovation. And somewhere in the California desert, a tiny beetle is walking over rocks. Indestructible, unbothered, perfectly engineered for survival.